Okay, so intro to logs. The main kind of thing that I want us to think about with logs is that a logarithm is the inverse function of an exponential. And because of that, it is really useful just to think of them as being exponentials. Okay, they follow very similar patterns. And we're going to kind of explore that with this first kind of introduction into what a log is. I think a lot of students find this confusing because they think of log as a word, and it kind of is a word, but I'm going to really push us to think of log as being an operation. Same thing as like multiplication, division, exponents. A log is just like the opposite here, the inverse of kind of exponentials or something with an exponent. They're really useful to help us solve for exponents. That is something we will do eventually. And they're used in a lot of applications, especially those involving large quantities. So I know like a really easy application that I can think of off the top of my head is how we measure like earthquake intensity follows a logarithmic scale. And those log scales show up all over the place. So there's lots of applications, and we will look at some of those later on in this unit. To get an idea of what a log is, we're going to actually start with its inverse function of an exponential, and we're going to graph both of them and just compare the two. Okay, so let's graph 2 to the power of x. That's something we've worked on already. Let's use values. I've got a lot here. So let's go -3, -2, -1, 0, 1, 2, 3. Okay, remember that 2 to the power of -3 makes that 1 over 2 cubed, which is 1/8. So then 2 to the power of -2 is 1/4, and 1/2, and 1, 2, 4, 8. And let's go ahead and graph this, plot all these points, a little bit more than what we usually do. So -3, 1/8, -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. When we're graphing exponentials, I do want to see that asymptote. Even though it's really not part of the graph, but it still just shows us that the graph is getting infinitely close to that line, but never actually touching it. And let's label this graph as f of x. All right, so one thing that I totally forget, I probably should have looked back to what we did first semester. Does that sound familiar to any of us? Did we do work with inverses first semester? I'm not seeing anybody like jumping at that sounding familiar. I don't think we did. So part of inverses, just an inverse is like the undoing operation, right? If I add 2, the inverse operation is to -2. So I've kind of already told us that the inverse of an exponential is a log. How we get there, we're going to get to in just a second. Other properties of inverses is that domains and ranges switch with inverses. And let's make a note of that, just because I don't think that's something we actually talked about. So if we have f of x, which is the original function, then f -1 of x is the inverse function. And that's the notation you're going to see. Okay, that reads f inverse of x. Here, f to the power of -1. Now, in our original function, we have the domain and we have the range. When we go to its inverse, what happens is the x's and y's are switching. In fact, that's how you basically find the equation of an inverse, is you switch the x and y in the equation and solve for y. So because of that, the range of your original function becomes the domain of the inverse. And vice versa. The domain of your original function becomes the range of the inverse. So by using that idea, we can come up with a table of values for this log function, where I can take the x's which are the domain. Okay, so if we take the domain or all the x's, those are now going to become the range or the y value. So I'm just going to copy those exact values over here. -3, -2, -1, 0, 1, 2, and 3. So the original domain became the range of our inverse. And the opposite is true about the range. The range of our original function becomes the domain of the inverse function, which is 1/8, 1/4, 1/2, 1, 2, 4, and 8. We're actually going to have a full lesson where we graph logs, and we're going to be doing exactly this. Coming up with the exponential table for the exponential, switch the domain and range to come up with points for our inverse function. So now let's plot these just to kind of get an idea as to what this looks like. So x is 1/8 and y is -3. So I'm going to go barely to the right and then down 3. Then 1/4, I'm going to go a little bit more to the right and now down to -2. 1/2, I'm going to go halfway and then down 1. I got 1, 0, 2, 1, 4, 2, and 8, 3. 1, 2, 3. And if we were to graph this, it looks like that. Okay, which is a very similar shape, just kind of rotated or reflected based on the exponential function here. So some things that happen here. One, you can kind of see that as we're getting closer to the y-axis, we're getting really, really close to that value, but never actually touching it. So with the log function, instead of having a horizontal asymptote, now we have a vertical asymptote. Okay, it's just kind of like the opposite from what we see with the exponential. So our domain is going to be restricted with logs. The range, however, can be any specific value, okay, or any value, period. All right, so that's kind of the extent to what I want to do with these graphs. Just again, to kind of enforce the idea that logs really are a form of an exponential. Okay, we'll kind of leave it at that. And so it's really helpful just to think about them as being exponentials. Also, okay, these conversations about inverses apply to functions, not just logs. They apply to any function that we've learned in here. Okay, that switching domain and range is how we find an inverse function. So some things to kind of pay attention to, because we've graphed exponential functions and we've talked about the domain and range. Well, with f of x, or the original functions, 2 to the power of x, we know that with exponentials, the domain is negative to positive infinity of every exponential. The range, however, is limited, right? It's limited because of that horizontal asymptote and because of the fact that we can't plug in any exponent and make that negative or even 0. So the range of f of x is 0 to infinity. And then the horizontal asymptote, that line is y equals 0. And now when you flip this page over, we're going to answer the same questions, but now for the inverse. So for the log function, which is log base 2 of x. Okay, so the graph of the inverse, the domain was what the range was of our original function. The range of the original function was 0 to infinity. So that's going to be our new domain. 0 to infinity. And again, if we look at that graph, we can see that. Okay, our log function is not going to go, one, it's not going to get to an x value that is 0, and it will never be negative. And that all comes back to what values we get with exponentials and the fact that the domain and range switches. Okay, so domain of our inverse is 0 to infinity. The range, this graph is going all the way down to negative infinity and all the way up to positive infinity. So for logs, the range is always negative to positive infinity. It's the domain of logs that is going to be restricted. And then what type of asymptote does the inverse have? It has a vertical asymptote. And that is written as x equals 0. Right, and all this stuff of graphs with logs, again, we're going to circle back to that. We're not going to get to graphs for a few weeks because of the testing week and us pausing to do some SAT prep. We're now going to kind of shift and really narrow in our focus onto evaluating logs and understanding what logs are. Okay, so starting with the exponential, and that's whenever you all come ask me questions about logs, I'm always going to bring it back to what we know about exponential equations. So just a reminder that with exponential equations, the domain or the input, the x's, those are the exponents or the powers. Okay, so domain are powers. The range is the result we get from the powers, okay, or from the exponents. There's got to be a better math word than results. I want to say product, but I don't think that's correct. That's something I'd have to look at. But the reason I want us to think of that is with logs, it's the opposite. The x values now are the results that we get from a similar exponential expression or function. And the range, so the y values are what we set logs equal to, are the powers. So logs are equal to powers. Logs give us the exponents. And we have a way of how we can rearrange log equations and exponential equations to come up with this idea. Okay, so every exponential equation can be written as a log equation and vice versa. These go in both directions. Notice that both have the same base b. So what I'm saying is that if we have a true exponential equation, like 2 to the power of 3 equals 8, that's true. I can write that as a log where it's log base 2 of 8 equals 3. Let's make a note of how I just read that right here. Let's write that this reads log base 3 of 1. And so again, what our log is equal to is the exponent. So this is the exponent. And so basically when I see log base 3 of 1, the question I ask myself is 3 to the power of what is 1? That's how we're going to evaluate that. And we're going to get to that in just a second. But again, this is really just enforcing that every log can be written as an exponential and vice versa. These go in both directions. That's one thing we will do is we'll convert them. And that's what we're going to do right now. Okay, so if I have an exponential equation and I want to write its corresponding log equation, how I remember this is I start with log. The base stays the same. So the base of my exponential is also the base of my log. So it's log base b. And then what you're going to hear me say is switch the position of the other two terms. So instead of it being log base b of x, now it's log base b of y, and it equals x. It equals the exponent. So my own definition, and if you have a better way to write this, maybe you come back to it after our lesson, what I think about is I keep the base the same. And switch position of the other two terms. Okay, and that goes whether I'm converting to a log to an exponential or an exponential to a log. Base will always be the same, just swap where the other two positions are, or the other two terms are. And to me, there's a really easy way to check this. Because if I hide the word log, let's hide it so you can see it. There we go with that. Doesn't this kind of look like an exponential? Doesn't that so? And so I can check that, right? Is the base the same? Is it still b? Yes. And are the x and y in different positions? Yeah, the y is the exponent here. X was the exponent in the exponential. Okay, so you're going to see me do that a lot. I'll hide the word log so that it looks like an exponential. I'm like, okay, is the base the same and are the other two terms switched? Okay, if we've done that, we've written the corresponding log and or exponential equation. And we're going to get some practice with that right now. So I'm going to flip this over. And that was a lot of introduction into logs. Now we're going to actually get to working with the logs. But before we do that, there's two special types of logs. One being base 10. Okay, so the logarithm looks like 10 squared equals 100. You will not see base 10. So what we're going to make a note of, if there is no base, that equals base 10. Right? With math, there's lots of invisible numbers sometimes. Right? If I just write like x, there's still an exponent there of 1. That's an invisible number I'm referring to. So no base equals base 10. Then remember that before we went on break, we looked at that continuous exponential growth, the PERT equation, and we looked at that number e. E has a lot of uses in logs, and it comes up with a specific log, which is called the natural log. So ln reads as the natural log. And it's all the same. It's the exact same as what we will eventually work with and know as regular logs. It's just a log that is base e. So if you see the natural log of x, that is the same thing as a log with the base e of x. So you won't ever see the base when I say natural log. Know that it is just a log that has that base of e. So especially while we're learning this, I might really encourage us to, if we see that ln, to just write log base e. When we see that base, it should make working with the logs much more simple. Okay. So let's get into some actual work with logs. And we're going to, a lot of this is how we view these types of terms, okay, or values. When we see log base 2 of 64, that equals just a number, okay? It's some number that we're trying to find being x. What I am asking myself in my head is I'm asking 2 to the power of what, that what being the really important part here, is 64. Okay, the answer to that is what log base 2 of 64 is equal to. Well, one way for us to kind of see this mathematically is to do that conversion, to take this log equation and write its corresponding exponential. So again, how I do that, I'm going to hide the word log here. So now this looks like 2 to the power of 64 equals x. So I'm going to write 2 to the power of the other term, x, equals 64. And now x is whatever that exponent is. Okay, that's getting me to that same question I'm asking myself. 2 to the power of what is 64? Some of these will be a little bit more obvious than others. But this one, I think it's like, what, 5? 2 to the power of 5? I think it's 6. 2 to the power of 6 is 64. So that means x is 6. And thus, log base 2 of 64 equals the number 6. All right, the next two, log base 7 of 49 equals x. When I see this, in my head, I am thinking 7 to the power of what, again, that what being the really important piece here, is 49. One way to see that, again, is to convert this to an exponential. So 7 to the power of x, so keeping the base the same, switching where the 49 and x are located, equals 49. I'm like, oh yeah, 7 to the power of 2, or 7 squared, is 49, and thus x is 2. So 7, log base 7 of 49 equals 2. In your groups, see if you can figure out what the logs of 3 and 4 are equal to. Those ones are a little bit trickier. You have to think back to some of your exponent properties to answer those. All right, number 3. Again, the way when I see log base 9 of 1, in my head I'm thinking to myself, 9 to the power of what is 1? 9 to the power of 0. For 4, the fraction, okay, because we're going 1/3 to the power of what is 1/27th, I'm really just thinking about 3 to the power of what is 1/27th, and that would be 3. Okay, so 1/3 to the power of 3 is 1/27th there. Any questions with how I'm thinking about evaluating these logs or any of the conversions into the corresponding exponential? All right, I know it's been a long day already. We're almost through this. I'll make sure we get some work time to start the block day lesson. All right, these next 4 are really the exact same. The only difference is they aren't equal to x. Okay, so if I see log base 7 of 7, I'm approaching this the same way. 7 to the power of a what is still just 7. Well, that would be 1, right? 7 to the power of 1 is 7. Thus, log base 7 of 7 is 1. If you need to, you can set this equal to x. I could say log base 7 of 7. Or let's do that for this next one. Okay. If it helps, I can set it equal to x and do the conversion if it helps us see that exponential. So I'll say equals x. The other weird thing here is there's no base. When there's no base, it's always base 10. I will encourage a lot of you to actually write that in, because now I can do my conversion. 10 to the power of x equals 1,000. That would be 3. So log base 10 or log of 1,000 is equal to 3. All right, real quick, see if you can evaluate 7 and 8. Again, this should take like 1 minute. Just think about it as an exponential. All right, I'm going to close these 2 out for number 7. When I see log base 12 of 144, I'm thinking 12 to the power of what is 144? That'd be 2. 12 to the power of 2 is 144. 8, same idea. I'm thinking about 6 to the power of what is 1? Would be 6 to the power of 0. So log base 6 of 1 is equal to 0. The rest of this assignment we're going to finish as kind of like our warm-up when I see everyone on the block. So we just got to this back page here and there's no homework assigned.